Cool. Yeah. So yeah, let's wait a little more for some other
No
people
worries.
to come.
What other talks have you had recently?
So the previous lectures we had were the introduction to recommendation systems and also introduction to, well, how to use natural language processing in recommendation systems. Yeah, so these two lectures I've hosted myself and with my partner Jeremiah, and yeah, it was pretty good. It's part of the competition that we're hosting, so that people who don't really have experience in like building recommendation systems, yeah, know where to start, where to look, what are the typical methods, and yeah.
Nice. That's pretty cool. So I'm guessing you covered things like cross-filtering type thing,
Yeah,
recommendation systems.
We went through collaborative filtering, content filtering, and also like hybrid models, and also looked into how to implement them like in practice. So how to do, for example, matrix factorization. What are the algorithms behind that? Yeah.
Nice. Okay. It's really cool.
Also, for the people who are here live, yeah, we brought some candies today, like last time. So yeah, feel free to take some. Yeah. Yes, maybe. Do you think I can connect to something here? Or? Huh? Answer?
Yeah. Which one? It doesn't matter.
So, it's from my computer. I think it should be good like that, maybe.
I guess you don't have too many people here.
Yeah, that's close. Yeah, so I guess we could start. Yeah, so hello everyone. Thank you for coming to the third lecture of the Machine Learning Fortnight. Today we have a company guest lecturer, JP from Weaviate. Weaviate is a company that does technologies such as vector databases, and I've also met their CEO recently in London, and yeah, they do very interesting technologies, very novel, and of course on topic of AI and machine learning. So yeah, thank you for coming, and I'll hand it over to JP.
Lovely. Thanks, Mensa. Appreciate it. Thanks for having me. It's really fun to talk to different crowds. I get to talk to a few different people as part of my job, and this is really fun for me. So my name's JP. My role at Weaviate is technical curriculum developer, but basically it's an educator role, right? So I get to work on things like the documentation, and I'm part of the DevRel team, so I get to build demos, go give talks at conferences and things like that. It's a very diverse role. It's a lot of fun. If you're interested in this area as a career, I would highly recommend it. It tends to, for me, blends like the technical aspect of the job, as well as like getting to meet the people in the community and reach out and actually make an impact, in visible impact, as I go and talk to people and things like that. So it's good fun. Yeah, and as far as what the company Weaviate does, it's a vector database company. So I'll start the talk by a little bit about databases, and then move on to kind of like the nitty gritty of all the different things that vector databases do and cool things you can do with it. Giving these talks is interesting, right? Because the audiences that we have for these types of talks really tend to be diverse. Obviously, I think I was trying to talk to Mansur about like where you come from and what your kind of academic backgrounds are. And that's going to differ from, so I assume a lot of you are computer science students doing things like machine learning. And then, of course, there'd be some of you doing software engineering and so on. And then these days, if I go to conferences, there tends to be a lot of developers who are just interested in the area in terms of applying these tools and techniques or as part of their software, development, right? So it's really diverse. And then there's database admins as well, too. So I'll see how it goes. If you do have any questions or like things you'd like me to sort of delve deeper into, I would love to do that. So just, come and ask questions, and then let's see how we go. But very broadly speaking, these are the things that I thought we could cover today, right? It's a very, very high level topic. So I'm going to start by talking about what is a vector database, and then all the things that make it a vector database, starting with what's a vector, right? And why use a vector database. And I'll get a little bit into like how do they work, but obviously all of these are individually very big topics. So we'll do what we can in terms of, what's interesting and what's not. But I've got a few demos here as well. So hopefully that resonates in terms of, hey, these are the things concretely that you can build with a vector database. So with that said, let's see if I remember my keyboard shortcuts, and let's move on to a demo. So this is a demo that I showed at a conference earlier this year. What it is based on is a quiz or trivia night, right? So the inspiration for this was that we had a company get together a few months ago, and one of the things we did on the evening was trivia, right? So if you've seen an American quiz show called Jeopardy, this is what this data set comes from. So it's like a collection of questions and answers. So let's look for some, if you have a particular topic you want me to look up, you can shout out as well, but let's look at things like space travel and then see what happens. Cool, and this is a real-time search. So if I type something else, I don't know, large animals, and see it's performing a real-time search, but let's try space travel for now. And there's probably a couple of things you'll notice here is that the query that I'm typing in, can you just give us a thumbs up if the font's big enough, or do you want me to make it bigger? I see some thumbs. Yeah, it's good. I think they're up. So you can see some of these questions are about space travel, right? So these transports first sent up in 1981, lift off like a rocket and land like a plane. So if you guess something like a space shuttle, you're probably correct. And you can see things like, yes, the space shuttle is correct. And that's the Jeopardy question. And the plural form's also acceptable. And if I say something like it's a Mario Kart, that's probably not correct. And I get an answer saying, hey, Mario Kart would not be deemed correct. A couple of things to think about is, well, what's happening under the hood when I search for the term space travel, right? What under the hood is the search mechanism that causes a question like this to come up, as well as these, and how you might build at the moment a search system that retrieves these results based on a query, right? How do you understand a query based on the certain words that I'm using? And then what am I getting back out? So we'll go through some of that. No surprise, I'm obviously using Weaviate at the back end to perform all of these. And then we'll dig through what is happening under the hood as we go. Cool. So that was my little vector database driven app. We'll come back to it as we talk about different concepts. But before we talk about vector databases, let's talk a little bit about databases. Can I just get a hands up if you've studied databases or used databases? Couple of you? Okay, good. It's kind of reassuring for me to be like, oh, good, I'm not going to be talking about things that you know more than me about. So that's actually a positive for me. So let's talk about a little bit about databases because that'll give us a little bit of an anchor as to where to start, right? So databases do a bunch of different things. You probably at least, if not used databases, but you probably at least familiar with them, like relational databases, SQL or SQL, and so on. So they do a couple of basic things. They store data, right? And it can be any types of data. So it can be for products, customer data, financial data, whatever. And it can be in a bunch of different media. So it can be text, images, videos, and so on. And you can do things with that data in your database. So if you hear people talk about databases, you'll hear the term CRUD, right? And that stands for all the things you can do with the data on your database. And that stands for create, read, update, and delete. So you need to be able to insert objects into your database, right? Because it starts off empty. So that's your creation. You want to be able to obviously retrieve it back. That's your reading. Your, say, customer data, your financial data, what have you, might change. So you need to be able to update it. And of course, things go out of date or your customer leaves or what have you, it's incorrect. So you need to be able to delete your data as well. So those are your core operations you perform. Now, of course, once you have that data in there, you probably want to be able to search and retrieve the data at speed because you probably know that if you have a database, it's not just going to be 10 rows of some sort of object. It's going to be millions, tens of millions, and so on. So you want some way of efficiently searching for the answer with high search quality and also do it quickly, right? So we all know that things, if they take too long, is not very useful, right, for the objective. So being able to do all of these things at scale is really a big reason to use a database. You might be surprised to know that database technology is older than probably everyone, including myself here, right? So if you've used to SQL or relational databases, that's about 50 years old, right? It's technology from the 70s. So things like Oracle, MySQL, Postgres, and so on are examples of databases. And of relational databases, that use SQL. And I would argue that actually things like library catalogs, right, are rudimentary forms of databases. And actually, if you do know about the Library of Alexandria, that was around 2,500 years ago, it held around 100,000 books. And the way they cataloged data, or the books, was through these little clay tablets that index where the books were, sorted by the author. So even then, 2,500 years ago, they were like, oh, we have a lot of books. There's no way that we can just go through these books one by one to find what we're looking for. We need some way to catalog this information, and so we can find it. So it was, some form of cataloging and indexing data so it can enable fast retrieval. So the next question is, well, it's 2,500-year-old technology. A SQL database have been around for 50 years. Is it solved? Is it basically like the wheel? Well, turns out no. There's new types of databases with new features and focuses coming out all the time, even now. So if you've heard of things like MongoDB, that's what's called a NoSQL database. There's Neo4j, which is graph database. There's an in-memory database like Redis, and Cassandra, which is a columnar database. And of course, which is Weaviate, and we are one of the vector databases. And as you've probably heard, there's this new fancy thing called language models. And the explosion of that technology has really made the interest in the vector databases explode in the last, say, a year or so. So it's been kind of an interesting journey for me personally to follow there as well. Why is that? Well, turns out storing data, cataloging it, and retrieving is a really, really difficult problem. And one key challenge is speed, right? So we talked about databases and said, oh, quite often you're dealing with tens of millions or billions or whatever of objects. So how do you retrieve these objects at an acceptable speed, right? So think about this query. How long, this is a SQL query. If you're not familiar with SQL, this would be looking at something like a table of objects of hotels. That's the first line there. And then the second line specifies one criterion where the country, you might have a country data column, and that matches the string Netherlands. How long might that take? Well, as CS students, you probably know that you probably don't want to look at each individual store manually, right? So there's going to be a linear order problem. If you have a billion objects, that's going to take a billion times as long as if you look through one. It's not scalable. So you don't want to do that. But what do you do, right? How do you make this scale? Well, a solution is to use what's called an index. If you've heard of the term index before, what it is basically an organization of your data, like a library catalog, to help up data retrieval. So in a library, you have the library catalog. I don't know if any of you have been to a physical library. I'm pretty old, but this is a thing that used to exist. You used to go to a physical library, and you might even have to look up library cards that were sorted in some sort of order, right? So you can look things up either by author, by subject, or by Dewey Decimal numbers, by category, what have you, right? So you have this thing called an index, and that helps you speed up retrieval and search. And in databases, you do the same thing. You have to catalog data in some way or another so that you can speed up the search and the filtering process. And it's the exact same thing-ish as what happens in a physical library, but it's just that it's done in the database, and it might be done in a slightly different manner. In a database, like a relational database, the most common type of this traditionally has been what's called an inverted index. And what that means is that it is cataloged by keywords, and I'm simplifying a little bit by saying keywords because it could be bigrams, it could be like tokens or what have you, right? It can be part of a word. But if you think of it as like, hey, here are some basic bits of strings, again, using CS terms, that's what you're cataloging your data for, and that's what you're searching for, right? If you think of it as like cataloging things by author, there'll be a form of inverted index by author name. So again, the actual thing you're sorting for is a token or some sort of like string, basically. And if you think about a book index at the back of a textbook, that's exactly the same thing, right? So if you look through the index in alphabetical order, you can look for those concepts and find where you need to go faster. And what this allows you to do is to circumvent the need to look through every subject because your data is pre-cataloged, right? So you're not doing these searches through your actual objects in real time, but you can retrieve objects, or you can at least find out where the objects are that you're looking for by looking through the index, right? And of course, that means your index has to be organized in the same way that you want to search for in your data, right? So if you've cataloged your books, for example, so I use the example of if you have a bookshelf. You've seen those bookshelves probably where they're sorted very, very nicely by color. Looks amazing on cut pictures and Architectural Digest and stuff. If you try and look for a particular book in that bookshelf, you'll go absolutely bananas because you'll never find anything. But it looks amazing. In the same way, if you have books sorted by author, like you go to a certain bookshop and you find things sorted by author, and you're like, oh, actually, if I want to find things by subject, that's problematic, right? So you have to have your information sorted in a way that aligns with your retrieval strategy. Otherwise, your index is not actually all that useful. So keep that in mind as we talk about search quality. What are some of the limitations of this approach that we talked about? What might this cause issues with? Like, what are the failure modes of this search strategy? Well, here are some that I've thought of. How would you cover typos? If someone searches for, say, Netherlands without the S, right? Or two Ds, whatever, would that work? How would you cover synonyms? Right? If someone said, oh, I want to look for Dutch hotels, Would that work? Don't know, maybe. Translations. Not all of us, obviously, all of you are, bilingual, which is amazing. I'm barely bilingual. But if you use, search strings in different languages, obviously in Europe, people speak many different languages. So it might not work if you type in the search string actually in Dutch or in French or whatever, right? So you go, well, what else could we do to solve this problem? And that's where vector databases come in, and that's where some of the benefits of vector databases are really handy. Can I just get a show of hands? This is cool that I can see you. If you know what a vector embedding is. 2.5-ish people. Cool. That's good. That's actually a higher percentage than what I usually get at a conference. It's usually like, I think last time I spoke was like a room of like 250 people or something, like 3 people raised hands. So it was like a non-zero number. But a vector, I'll start with what a vector is, and then I'll move on to what a vector embedding is, and so on. Because it's a very, forgive the pun, it's a fairly dense concept. And people tend to overcomplicate it when they explain it. So I'll try and see if this makes sense to you. And you can ask me questions if this is all nonsense. So a vector is just a set of numbers. And if you've done science, you might think of vector as a scalar with a direction, right? Like that's not what we mean. This is a kind of a mathematical vector. So it's a set of numbers. So 2 numbers like this is a vector. You can have a bunch of floating point numbers like this. That's also a vector. We can have like a whole lot of floating point numbers. I've got an ellipsis in there. So if you have like 1,000 of these, 10,000 of these are all examples of vectors. Sounds pretty simple, right? Well, in a vector database, those are used to represent meaning. And this is where, depending on how deep you want to go down the rabbit hole, it starts to get really hand-wavy or just really unnecessarily complex. So I'll try and thread that needle in between. And where people tend to get most confused is when we say, hey, we have a bunch of numbers. We use that to represent meaning. And that's where the disconnect begins to happen, because you go, well, how do a bunch of numbers represent any kind of meaning at all? And I would argue that many of you have probably seen this before in some shape or form. And here is like a fairly common example that most of you, I think, would have seen. If you've used RGB numbers in Photoshop, MS Paint or Canva, whatever, you're probably familiar with the system of, RGB numbers. You have 3 numbers that represent colors, right? So you have 25500 for red, 8200 120 for emerald, and so on. And in this system, you can think of each number as a dial, right? You've probably even seen the RGB color selectors where actually each number is set up as a dial that you can just move up and down in a slider. And moving each one would change the actual overall produced color. And each of these numbers change the dial for how red, how green, or how blue that particular color is. So now if I plot a bunch of colors in 3D space by their red, green, and blue values, this kind of cool thing happens. Like these colors that I've shown here are just outputs, if that makes sense. So these dots are not organized by color. These dots are organized by RGB values. But what happens as a result of that is that those similar colors end up next to each other, right? So, clicked on the wrong thing. If you squint a little bit and extend this concept to, let's say, what happens if I have hundreds of these dials and thousands of these dials? And instead of an 8-bit number, what if I had infinite adjustability with floating point numbers, right? Instead of an 8-bit integer, excuse me. So that's how in modern deep learning or in language models, vectors are used to represent meaning. So here's an example of a headline. So it says 3 people rescued off Australian coast after yacht damaged by multiple shark attacks. I'm Australian, and this is like the most Australian headline ever of like people getting attacked by sharks on the coast. So I love this headline. And if you convert this to a vector using one of the models, you just get a bunch of numbers, right? And I can do the same thing with these other headlines. So the second one is, again, an extremely Australian headline about tourists taking selfies and feeding dingoes. And actually that fueling a rise in basically like dingo attacks, which is, again, an extremely Australian tourist thing to do. And then the next two are about star players at the last World Cup, Women's World Cup that was just a couple of months ago, right? So Sam Kerr is the Australian captain. So this is a story about her. And the last one is about Mary Earps, who's the English goalkeeper. And each of those can be converted into vectors. And these are OpenAI vectors, so they're 1536 dimensions. So there are, in this particular case, a Python list of 1536, I believe, floating point numbers, right? Okay, still, so what though? So you've converted a bunch of letters into a bunch of numbers. Why does that matter? Well, the cool thing now is that I can compare them. So I can, because they are now numerical, they are quantifiable, and I can compare how similar each of these are. So if I plot a similarity matrix between those 4 headlines, these 4 bits of text, this is what I get, right? So the similarity matrix, hopefully you're relatively familiar with something like this. So it's symmetrical about the diagonal because you're comparing each of those 4 headlines. And, so each second row, first column is a comparison between the second and the first headline. So you can see that the top left quadrant and the bottom right quadrant are relatively high values. And it intuitively makes sense, right? Because the top 2 are about Australian tourism-related headlines, and the bottom 2 are about football players. And across the bottom left and the top right, they are quite dissimilar. And that's the magic of vector embeddings, is that you are able to capture the meaning of text into numbers, and then you can manipulate them. So I can put these into, obviously, I can't plot 1536 dimensional space on PowerPoint, unfortunately. So if I dimensionally reduce them, they look something like this. And similar kind of thing that we saw with colors happens with text. If you organize them by their vectors, the ones with similar meaning end up next to each other. So apologies, I think the text is definitely too small, but on the top left-hand corner, you see words like wolf, dog, and cat. On the right-hand side, you see words like banana and apple. So you can see it's similar, I guess, animal-related words on the left, and sort of fruit or food-related ones on the right, and they end up grouped similar next to each other. And what's happening in terms of getting these vectors, this is the job of AI or deep learning models. And that's why the field in the recent past has made such advances. It's because it advances in the field of deep learning. And over the last approximately about 10 years, I would say, the field has come such a long way that you can do things that basically were not imaginable in terms of natural language processing and being able to manipulate words and other objects, as you'll see later, by their meaning, which is really, really cool. And here's, it took 25 minutes to get here, and this is what enables vector search or search by meaning. So in a vector database like Weaviate, they use vectors to represent the meaning of objects, and that allows us to search those objects. You can even do some transformations of objects, as you'll see in a bit. And this is the same underlying technology that is used in large language models. And the architecture of these 2 models, the ones that produce vector embeddings, and the ones that just spit out tokens or words like GPT-4 or what have you, very, very similar. They do slightly different things in terms of the final outputs and how they're trained and so on. But the vector representation or vector embedding representation of meaning and words is really the key to a lot of this. So let's go back to our discussion of the index, right? So we said an index earlier is a catalog of information. So a vector database or vector databases have vector indexes. I need to get my singular plural tenses right, but that's okay. So indexes organize and catalog data. So a vector index is an organized catalog of data by meaning, which is your vector embedding. Right. So the process is to go and retrieve or generate those vectors and organize them. And I might not get into like the how of generating these vector indexes, but then it's not just a simple storage of these vectors, because again, you have the same problem of scalability. If you just simply store these vectors and if you need to look them up one by one, that's not really going to be tenable in terms of scaling to millions or billions of vectors, right? So there's what's called proximate nearest neighbor search that happens that allows fast similarity searches. And what that does is, at least in our case, there are a number of different ANN algorithms available. The one that we use in our software Weaviate is called HNSW, Hierarchical Navigable Small World, I believe is what it stands for. And basically, it indexes your vectors so that you build these layers of simplified representation of the vector set so that it makes traversing through the vector space faster by being able to not having to look up or not having to compare as many points at the higher layers. And then as you navigate those graphs and get to the right regions, you can then do searches along the lower layers where you're starting off in the right region. It's like a 20-second summary of a fairly intricate and complex CS algorithm. So excuse me if I butchered any of it, but this is a really interesting area, and different algorithms or different indexes use different algorithms to perform this job. And there are different algos available for different problems, right? So HNSW is really good if you have lots and lots and lots of data. But of course, building these layers and the additional compute required for all this, and also these additional layers requires more memory and compute resources and so on. So if you have fewer objects in each collection, you might not need to do this. And another type of like flatter index might be more suitable. And of course, is this being an approximate nearest neighbor, there is a slight cost to things like recall, right? So it's not a perfect search. So you need to trade off different parameters as to how high you want your search quality to be versus speed. So just like everything else, it's not perfect, but it gets you pretty close a lot of the time. And yeah, it's amazing. So as an example, about a year ago now, a colleague of mine built a data set with about literally a billion objects in the database. And I think the search was still taking basically like half a second each, or maybe less, I think. So it's pretty impressive, right? You're certainly not going to do that in a NumPy array with a billion objects if you can fit that into memory. So this is really, really cool stuff. I will mention one more thing, which is that, hey, a vector index is not a vector database, right? And I say that, hey, this is the analogous to saying a library catalog is not a library. Like, just because you know where to find certain things, it doesn't mean that you actually have the underlying information and the data. A database houses and manage the collection of data, and an index is usually a part of that database that exists to improve, remember, the speed of data retrieval by cataloging that information. So that's something to remember, because there's libraries out there that are just simply indexes, like things like FICE come to mind. This isn't to say that like one's better than the other, but they just do different jobs, right? So just keep that in mind when you see the nomenclature out there and discussions, because this is such new technology that I think these terms get used interchangeably. And to be honest, quite often these terms evolve pretty quickly too. So I'll talk a little bit later about something called RAG, Retrieval Augmented Generation. You probably heard that term recently. And that term basically, didn't exist like 3-4 years ago, right? and we used to call that something else, but these things change really, really quickly. Okay, so let's talk. Does anyone have any questions so far? Nope. Cool. Okay, let's talk about searches a little bit. So this is a typical workflow in a vector database. It's a fair bit going on here, but typically you start off with either the data or the query. You probably need to start with data because you have to ingest data into your database at some point. And the data needs to go through some process. I'll go through that a little bit to be encoded into a vector that gets stored into your database. And then once your user performs a query, that query also needs to get turned into a vector so you can compare apples to apples. And then you perform a search and you get a series of results. A vector database, the exact capabilities differ a little bit depending on exactly what database you're talking about, but I can talk about Weaviate because that's what I know and that's where I work. So Weaviate can perform all of these types of searches. It can perform vector searches, keyword searches, hybrid searches, and filtering. And don't worry if you're falling asleep. I'll show some of that in a Jupyter demo in just a short while. Let's talk a little bit about vector searches. So this is what I was talking about, right? So I'll go through the different searches and run through how they are different and what they mean. So a vector search is looking for things that are most similar in meaning, right? So you saw that graph earlier of the different words in vector space. So I would say, hey, I want to find objects that are the most similar to the word puppy. And what would happen then is I would use the same model that converted the word, all these other objects into vectors to convert the word puppy into a vector, right? And I would use my approximate nearest neighbor index to perform my search. It'll say, okay, puppy is about there. Here are your n most similar objects. And there you go. Right? Hopefully that's now fairly simple. And then there's this thing called keyword searches. And if you use SQL, this is a little bit different to what you might think of as a search in terms of the where clauses in SQL. I tend to describe it as cases where your keyword terms are the most relevant. And what I mean by that is it's not just looking things up in terms of matching a word. If you think about what happens in the back of a book in an index, it doesn't really tell you where those words appear. Like if you look at an index at the back of a book, it's not telling you where those words, like every page where those words appear, right? It's telling you where those concepts can be found. And a keyword search does something similar. It depends on the exact algorithm, but basically what we use, something called a BM25, is a weighting of, actually I might just pull up that formula. So what's called a BM25, you can look this up yourself if you're interested. I tend to not do this in talks because it really tends to put people to sleep. But it's a technique based on what's called a bag of words. And this is what we used to do back in the day when these deep learning models didn't really exist, was basically like you would create an index by counting words that appeared, right? So you say this word cat appears 15 times in this document, whereas appears 12 times in this document, 3 times in this document, and so on and so forth. And the same with every word that gets indexed. What you can do with that, then, you can imagine then a couple of things. One is your vocabulary that you're indexing is going to be huge, right? If you have 10,000 documents and you're indexing for every word, this is a huge thing to do. And that's going to produce what's called a sparse vector, right? Because mostly there's going to be a huge vocabulary. Many of those words don't really appear anywhere. And then what you're going to do is perform what's called a TF-IDF search. And that stands for term frequency, which is how often that particular term you're looking for appears, and an inverse document frequency. And you can think of that intuitively as how often is it like supposed to appear, right? So that kind of normalizes how often that term appears. If it's like a word like A, let's forget about things like stop words. The fact that the word A appears a lot doesn't mean anything, right? Because it kind of appears a lot everywhere. But if you say, look, the term radiology appears a lot somewhere, that probably means quite a bit because it's not a very common word to use, right? So that's the intuition behind these keyword search functions or sparse vectors. And a BM25 is a variant of that, where some of the weights are, I believe, capped. And then what we use specifically is what's called BM25F. Let's see how good my search skills are. Cool. BM25F. Again, none of you need to know this unless you're doing information retrieval. But basically what this does is it weighs different fields. So you can imagine if something appears a lot in a headline, that means probably a different thing to something appearing a lot in, let's say, the body, right? Or the appendix or what have you. So that's what BM25F allows you to do, is to weight those fields. So that is, oh no, I've lost where I am. That is keyword search. I found it. So it's not just, hey, does that word appear? It's how significant or how relevant are those terms, right? That's keyword search. And there's this really cool thing called hybrid search, and you're going to laugh at the next graphic, which is very technical. So if I look for a hybrid search for vacuum, you get this. I know this is an extremely technical figure, but basically what it does is to perform 2 separate searches under the hood. So at least in the case of Weaviate, it performs a vector search, just with the same query term like we talked about. So convert the query to a vector, get the objects, and then performs a keyword search as well under the hood. And what it does is combines them using what we internally call a fusion algorithm. So there's a couple of different fusion algorithms. In one particular option, you would get ranks. So basically the top and objects, and they get combined based on where they're ranked. So if an object appears at the top in both of these searches, that's great. They tend to be at the very top of the search results. And it tends to favor results that are very high in one or the other, right? So if it's like really high in one, but not so high in the other, they tend to rank better than results that are like in the middle in both. And this is a really good way to complement either of the search approaches, because what tends to happen is that and you'll see this when you start to work with real data sets, is that as text gets longer, or as you start to have kind of more diverse data from different domains, the word matches, which you might not think matters so much, starts to matter more. But at the same time, you can't always be sure that the author used the same words that you want to use. So, neither of these approaches are perfect, and a hybrid search kind of gives you does a pretty good job of balancing the needs or balancing the weaknesses of both these searches, so you end up getting quite good results. And then there's a filtering aspect, right? So a filter would say, hey, only give me results that were made in certain areas. So if I want to filter, so basically if you're thinking about a set of conditions, that a filter meets or not. That's what a filter is. So this is exactly what a where clause in SQL does. And as you probably know from using SQL and where clauses, there's no inherent ranking you get from where clauses, right? It's like you either have to have a sort by, or you just get like some sort of default result by index or something. So quite often what you'll do is combine a filter with a vector search. You can say, hey, find me, this was on top of my mind when I made these slides because I bought a vacuum recently. Find me objects that are most similar to automatic vacuum. So that's your vector search, right? Because you're looking for similarity. But only find things that meet these criteria, which in this case is to only look in products made in the UK. So that might say, hey, look for match these conditions in your search. What I was going to do, I think at this point, was going to do some live coding. Do you have any questions before I do that?
I think I had one question. Yeah, just going to close it a little. So
Sure.
I think in the beginning you told that vector databases could also be used, for example, like on new types of data, such as, for example, images. So I wanted to ask, when you actually perform like a search of images by text, for example, also like a vacuum cleaner, for example, how does it actually embed, for example, text into this image space, and how does this work? Because I don't know how, or for example, you cannot really use TF-IDF to search for images. So what is the process here then?
Yeah, it's a really good question, and it's really interesting area. So let's see. So you're actually getting into this topic of where embeddings come from. Let me see if I can, what's the best thing to do? Skip slide. So maybe I'll just talk about it briefly now. So what it comes down to is what model you use to create those embeddings. And I said earlier when I started that I was going to do a fair bit of hand waving, even though this is probably a little bit more technical than I get into. What I didn't cover at the moment or so far is what it means for something to be similar, right? So if I said, oh, I am similar to Brad Pitt, they might go, what the heck are you talking about? And I might say, well, I'm more similar to Brad Pitt than I am to my pillow because we're both humans, right? Okay, so that's one thing. Or I might say, I'm actually more like my pillow than Brad Pitt because we're in the same area, right? So what I'm getting at with this fairly silly example is that similarity depends on your criteria. And that's what your model that creates embeddings determines. And I'll talk about this in this next section. So in terms of your particular question about, those are called multimodal models because data scientists like using words that are very difficult to pronounce. What that means is that you have a model that embeds both images, or in this particular case, images and text into the same vector space. So have you seen a model called CLIP, or a class of models called CLIP?
Yes,
yeah, for those of you who might not have, oh my gosh. So this is the class of models called CLIP, developed by OpenAI. And the kind of really, really clever thing about that was that I believe, I'm going to butcher this, but I think basically what they've done is to scrape data with a bunch of images and the text that is associated with those images. So then you can train these models, because we could already train images into embeddings, right? Because it's just at the end of the day, a neural network, right? You have a bunch of inputs and you have a bunch of outputs, or one output depending on what you're doing. Regardless, and that's the same regardless of whether you have text or images or audio or whatever. The challenge there is, how do you train your model so that your goal, right? So your loss function looks for the same output, whether it's the image or the text. So it knows that it's the same thing, or text versus an image or a description of an image. So the clever thing people are doing now is to say, oh, we've got an internet full of images, and we've got also an internet full of, like, say, alt text or descriptions of those images. And they were able to use those to create a model that, regardless of whether you put in an image or the text, kind of gets to the same embedding, the same vector space. And that's the sort of cool thing about vector databases, is that, so in terms of what we do as a company or vector database companies do, they're not usually in the business of making models, right? So you have to choose a model that works for you, depending on your goals. So if you're looking for, if your use case involves images and text in the same data set, something like a clip model or something called an image bind model, which is even more multimodal. So you can actually, like, relate things like videos or even like accelerometer data. To be honest, I still haven't quite wrapped my head around what accelerometer data should, like, what image or what, like, text and accelerometer data should get me. Like, that's kind of beyond my little brain, but you can theoretically do something like that, right? So that's what a different model gets you, and that's what a clip model in this particular case allows us to do, is to embed these different modalities into one space, so you can search images by text and text by images and so on.
Thank you for answering. It's very
Cool.
nice.
Yeah, it's a really good question. One of my colleagues actually did a talk entirely on multimodal models. Zen, he's really into this space. He's a data scientist. I think, yeah, so you should be able to look up some of the talks he's done on multimodal models if you're interested in this space, for sure. Okay, I'm a little bit cognizant of time. Do you want to have a short break and then come back? What do you think?
Yes. Yeah. Let's have a 10-minute break. Or
Yeah,
yeah. Okay.
sounds good. All right, cool.
Come back at
Thanks all.
10 minutes. You want some candies? Yeah, I brought a bunch of candy.
Amazing, yes.
Do you want one?
Oh, thank you. It's very delicious.
There you go. That's very nice. If you want, you can take more also. Like they are available there.
How was it look over the weekend?
Pretty good. The competition was very nice, and there were a bunch of companies that we got to talk to.
Nice.
Also looking for sponsors for Pepsi and Pepsi for next.
So you look.
No, they all agreed with me. And you never know until something got proposed actually.
us for different images. For me, it's like the first month that I actually do stuff like this. So it's a bit of a long process. Right? Takes me a little bit to understand what I'm doing.
Yeah,
But it is interesting to finalize things.
nice.
Like we came here because otherwise we know that otherwise we don't apply really the knowledge that we give you. At least if you have a deadline to meet, you're gonna just be there for the day and try something with.
Yeah, that's nice to hear. And yeah, that's also the reason why we also host these competitions and the like lectures overall, so that everyone can apply their knowledge, because our university is like mostly research based and not a lot of practice actually is going on through. So yeah, for example, having events like these helps a lot, I think, for the students.
Yeah. And I don't know, like I feel like there's very little people also for the weather.
Yeah, like the participation is not that high.
Yeah. Is it also like usually like this?
Last year it was 60 people, like every lecture.
Yeah, right. Like
It's crazy.
like I remember coming here last year and like not understanding anything, but there was a lot of people.
Yeah, I think this period overall is like much harder also. Like
Fair enough.
me and my friends are doing their thesis and yeah.
I mean, but I'm happy that I'm understanding
Probably
compared to last year.
That's great.
Nice.
Nice. Also, like in the second part of the lecture, I think we'll be going more through actually demos and how to apply, how to actually build it like a vector database using their technologies. And I've seen a few demos online. It's actually quite nice.
Actually, that's something you don't really, you would apply more in a work space and that's not in what we are doing right now. Like somewhere where you actually have a shit on a day-to-day work.
I mean, have you done software engineering?
No.
No. Are you AI or CS?
AI.
Ah, okay. Never mind that. Yeah, so some of the projects, some of the companies also require processing data such as like unstructured data, for example, like images and videos and text. And in most cases it's not obvious how to do it. And now we actually have the technologies to do so. And so it's nice for people to try out new methods. Learn about it.
Maybe can you hire the volume next time? Or is that max?
This is my max.
Yeah.
I'm so sorry. Like, I would love to connect to it, but like, I don't know how. Maybe I could connect like.
CS student.
Yeah, I'm AI student.
Oh, AI student.
Yeah. You're also AI, right?
Yeah.
Are you second year or
Second.
Second. I see. Yeah. I might look into switching the computer to this one, but I think it is dangerous. I'm also recording this, but I'm not sure even if I'm actually recording the correct display. I selected display 2, and I hope it's that one, because if it's my calendar, that's not cool. You're Tion, right?
Yeah.
Did I pronounce that right?
Turn.
Turn.
Yeah.
Okay.
Close enough.
Did you get my email?
Oh, I see everyone's still there. That's good.
Yes. Yeah, maybe we can talk about that later. But
Do you have any questions in the meantime?
You guys, do you have any questions in the meantime?
I'm not sure.
Nope. Okay, then we could continue if you're ready.
Cool. Sounds good. Do you not have any questions just because you're terribly confused, or is it all making sense so far?
Do you not have any questions because you're terribly confused, or is it because
No,
you're
that
sending?
makes sense.
said he's gonna come to the lecture, but
It makes sense.
all right. Yeah.
Cool. Thanks very much. All right. Sounds good. Where were we? All right. So what I think would be useful at this point is for me to have too many tabs open, and let's do some live coding because I feel like that could be useful. So we can go through some examples of different searches, right? So and then let's go from there. Cool. Do you all code in Python, by the way, or like is Python kind of
Yes.
sensible enough for you? Just give us a thumbs up if you Python's okay. Fabulous. Like, is it your primary language you code in? Is it something else? What do you typically code in?
So right now the whole program is trying to switch to using Python for AI specifically. So
Yeah,
Yeah.
it's pretty much Python.
yes, literally everything is in Python now.
A bit of
Okay, what was it before?
It was in C and like OP. We had like in Java, for example. It was every language possible, and yeah, now everything is centered mostly in Python. So we have like signals and systems in Python, and algorithms and data structures. Yeah, all of that is in Python, and I think that's a very good change for the program itself.
Wow, that's interesting. Going from C to Python would be a big change for everybody.
Definitely.
Yeah, cool. All right, well, I'm glad that this is going to be sensible. I was tossing up between using JavaScript and Python, but I figured, yeah, Python would be more common. Cool. So what I'm doing here is I'm just going to go through some different search types so I can get a feel for what the results look like given different searches. So I think this notebook's still running. Yeah, so I've just created some helper code, or at least some instantiation code, so I don't bore you with that. So all I'm doing here is connecting to a Weaviate instance or local database that I'm just running on my computer, right? So it's just kind of connecting to localhost under these ports. Don't worry about any of these details. And what I'm doing is getting a collection. A collection in Weaviate is basically like a table in SQL, right? So I'm just connecting to essentially the database here and instantiating an object where I can communicate with a collection of our quiz items. And this is just helper function that I'm like producing because the queries that I run will have a particular data type that comes back or class. And then I've just got, this function to dump the results on the screen. So if I run this, I guess I didn't run it. If I run this query, what I'm doing is at the moment, just fetching two essentially random objects, right? And you can see that I've got a limit parameter here. So is this big enough for me to make it one larger?
It's good.
Good, cool. So what I'm doing is I've got a limit of 2, so I'm grabbing 2 objects, but I haven't specified any other parameters, right? So I'm just getting 2 objects from the database, and they each come in a JSON format or dictionary format like this. So you can see some like bibliographical information like points when aired on TV. And the key things I'm looking for are the answer, which is obviously the answer to the question, and the question. So let's have a look at those and see how they change based on our different queries. So I'm going to say response equals collection dot query. So let's start with a keyword search. So that's called a BM25 in Weaviate. So I'm going to specify a limit. Oh my goodness. Query. Let's look for, let's say, space. I'm a big space nerd. So, and I'll use the same helper function that we defined. Oh my gosh. There you go. So I've searched for the word space. And interestingly enough, well, not interestingly, probably actually, you get results with the word space in the answers. And they score well because remember, we talked about the BM25 F formula, as I'm sure you all remember. It weighs the significance or the relevance of these words in each field. And because in these particular answers, the word space appears as a high proportion of the entire field, that scores really well. And that's why we get these results. And now if I use a synonym, like the Beastie Boys song, I'm not going to get any results. Look at the response, it's actually just a null list or an empty list that I've got in the results because it's not matching for that word and it's not finding anything. And the same thing kind of happens regardless of what word I search for. It's basically going to search for these things, these objects based on my query and the scoring metric. And if I actually take another look at the response here, that's probably a bit messy. Yeah. If I look at these, oh, okay. So if I look at this result now and I request something called a score, don't worry about the syntax, right? Because you can just look that up in our documentation. You'll see this thing called a score. And in a BM25 search, that is your BM25 score, as in how well did this object match our query. So that's a BM25 query, BM25 search. And now let's try something different. Let's try a vector search. Call that a near text search. And just want to make sure that I think that's right. Nope. Sorry, this is a beta client, and I quite often get a query. That's wrong. Oh, right. Oh, yes. It's headers. So what I'm doing here is, in this particular instance, I'm using the OpenAI API to generate vectors. So remember we talked about before that when I insert objects, the objects need to get converted into vectors and you need some model to do that. So the way I did it for this particular instance is to use the OpenAI API to do it with their default model, which is ADA 002. Now, when I run these vector search queries, I need to do the same thing so that the results are in the same kind of vector format, right? Or vector, are the outputs of the same vectorizer model as the inputs. And because I screwed up, I didn't provide my OpenAI API key. I need to do that. West. Nothing more exciting than watching someone else get the API key. That should work. Cool. And if I run this query again, so I'm just going to delete that cell. Cool. That should now. Did that not? Oh, I have to get the collection again. There we go. That should work. Cool. So now, if I search for the word history, we get different results. And interesting things start to happen. You'll see that now in this answer that we get on the top, the word history doesn't quite appear like you get the word historian. Oh, so it does appear on the top one, sorry. But at least in the second one, the word history doesn't appear, right? And what you get instead is something about some sort of an old French something or other. I'm kind of interested because that's not typically what I see when I run these searches. So I don't know what's going on with the data set. But still, the point is that before, what we were doing was searching for a particular keyword. and it was only matching the particular word that was matched and how often it appeared to derive a score. But now what's happening is it's performing a vector similarity search, and we're getting, even though the actual keyword doesn't match. If I search for the word intergalactic now, you start getting these different results, and these are two distinct entries, by the way. I know the answers are the same, but obviously the queries, the questions are different. So even though the word intergalactic doesn't appear anywhere, we start to get these results. And if I go further or move on and do the search for a hybrid search, let's see what we get, and let's get a few more results. So we start to get, actually this is probably not a good one because there are no word matches for whatever. So we start to get these results that are a blend of, let's look for the word history, sorry. We start to get results that are a blend of the searches that are keyword searches and vector searches. And this is still the case regardless of how long a search string I put in. So the first, I don't know, vehicle to travel across space. So we start, even though I'm searching for this very long keyword or this long string, I get these results, and some of this would be based on the matches of the keywords on VM25 formula, and some of these would be based on our vector search. And I can see that by grabbing our metadata. Need a comma. Score true, explain score true. And if I look at zero, cool. Maybe I should just look at explain score. So, sorry, trying to get the formatting right. So what, if I look at the first result and look at this explain score, now we're working on cleaning this up a little bit because the results aren't clear, but you can see there's components of it that come from the vector search as well as the keyword search that contribute to the overall score of the result. And that's what determines the entire ranking. Again, the exact syntax of the search or the exact scoring mechanism doesn't matter so much because you can always look that up as a reference. But my point here is that there are these different search methods available that give you these different flexible outputs. Because if you look for different, in different circumstances, different search results will work better than others. Cool. So let's go back and talk a little bit more about embeddings because I do want to get to that, and I do want to go and show you RAG and maybe talk a little bit about recommendations. I know you guys are interested in that space as well, but see how we go for time. Cool. Let's talk a little bit about where embeddings come from. So we talked about this, right? So we have some sort of documents, images, whatever, and you get to embeddings. And the answer is deep learning models, as we talked about briefly. And this is the process of importing objects into a vector database, or Weaviate in particular. So you start with data on the right-hand side, and if you have the actual vectors to go with it, you can just send your object and your data to Weaviate directly, and it gets stored happily into Weaviate, the data store, and it builds a vector index. Or you can, if you don't have a vector, you can use a system that's built into Weaviate where it will generate or at least get a vector for you, right? So if you send the request of just with the data payload without a vector, from Weaviate, you'll get a request for an object vector into one of its modules that you've got configured. don't worry about the exact module system, but just understand that in some vector database systems, it can take care of that because it's all integrated. So that it goes, okay, I want to store a vector along with my object. I don't have that, so can I get it? And in my particular case, what I've done is to go to an inference API, in this case, the OpenAI one, request an object vector, get the vector back, and dealt with it. Now, it can just as easily be a local model. We have a transformers module, which uses the Hugging Face transformers library, which many of you probably have used already. And it uses that under the hood, and it does local inference, and you can get the vectors that way. So that is a way of saying you can use any of these tens, if not hundreds of models that are available. There are these days a ton of proprietary models available through friends at Cohere, OpenAI, Google, AWS now have vectorizer models available, and so on. And of course, there are all of these open source models that are available from Hugging Face, right? Some of the more popular ones being, all your sentence BERT based models that's been around for a while, and the new ones keep being developed. And you'll even find that there are these specialized models that are fine-tuned for particular domains like legal, medical, and so on. So why so many? And this is the question, we had just before the break about what do you do in cases when you have a image or multimodal situations. So here's a question for you, and we've talked about this a little bit. Which two out of those four are the most similar? So you got puppy, you got a cute furry brown dog, you got an actual picture of a cute puppy, right? Or the French word for puppy. Which of those two are the most similar? Well, some might argue, if you're an English speaker like me, you would say, well, these two are in English, right? So a puppy, a cute furry brown dog is almost a puppy. They're very similar, certainly. Well, if you're looking for something that best matches an image, you would say that description on the left, which is a cute furry brown dog, is the most descriptive, right? Text that matches the text, so the image. If you're bilingual, as I'm sure many of you there speak French, a puppy and chat is the closest matching pair because they are literally synonyms. But of course, if you don't speak French, that probably doesn't mean much to you. So what I'm getting at with this example is that which two out of these examples are the most similar is determined by the model, right? Because the model makes the decision as to what features to capture and what to output as your vectors. And here are just some of the models that are available that will change or convert input objects to vectors. And obviously this is not even close to being a comprehensive list of vectorizer models. Some are quite old, but I thought I'd give you a flavor of some of these models to talk through to show you that, hey, this has been going on for a while and there's just a big wide world of models out there. I'll talk about some of the more significant ones, right? So I think really for me, I remember when, that's a typo, excuse me, the word2vec model was from 2013, not 2023. But really the impressive thing was, it was one of the first models that really popularized the idea of converting individual words into vectors. And if you've seen this kind of vector maths before, where you say king minus man plus woman is roughly about the vector for queen. And you can actually just perform, arithmetic like this using the vectors you get out, right? So these are vectors shown as barcodes. And if you subtract, man from king and add woman, you get this vector on the bottom. And if you kind of squint a little bit, it's pretty close-ish to the vector for queen. And you can kind of see where this is going from, right? Like the difference between the vector for queen and the vector for woman would be some sort of vector for denoting royalty, right? And the same difference that applies to king minus man equals, queen minus woman. So that really opened people's eyes as to, hey, this is really powerful. You can convert meaning and capture meaning as a series of numbers and manipulate them. And we can skip a few years to the BERT model. And that was kind of the other really, really significant development in the space, because if you hear the word transformer a lot, and that's the T in GPT, BERT was one of the first successful transformer architecture implementations. And what that allows us to do is to capture the context of words. In word-to-vec implementations, all the embeddings for words are independent of each other. And that makes capturing meaning of sentences, paragraphs, and larger pieces of text very difficult, right? Because words, as you all know, don't have just one meaning. It depends on how you use it, depends on what words come before and after it, and depends on the context. And what these transformer models allowed us to do, or allowed these models to do, was to modify words based on what happens around it. So if a word bank appears around the word river, it means it's completely different to when you talk about a bank heist, right? A river bank is basically a body of dirt that, is on the side of a river. And whereas a bank heist, in that sense, a bank is some place where you hold money, kind of. So a BERT model, or these transformer models, were able to capture the context. And this really was a big, big change in terms of how you could capture meaning in longer forms of text and manipulating them. And then CLIP was another really interesting one, because it was a very popular multi-modal model, like we just talked about, and allows image and text and multimodal comparison. So exactly what we talked about before the break and just now, you can compare similarities across a picture against ones for just the description of that picture, which is really cool. And then there's other ones that are really cool, like the Cohere multilingual model. This is pretty self-explanatory. It's multilingual, so you can search for, kangaji, which is Korean for puppy, as puppy, and so on. It actually speaks, or I have to stop anthropomorphizing these models, but it's able to transform or convert inputs in up to about 100 different languages into basically the same vector, which is really, really impressive. And think about in workflows, how much that would change what people do. So, think about armies of translators working on certain jobs. If you think about data sets on things like Amazon, you can quite often see these days the little button on the reviews and say, translate this. And all these models, probably not necessarily this one, makes that job much easier. So if you imagine aggregating all that review information that companies like Amazon would have, now you don't need to translate them all before you aggregate it. You can just convert them all into vectors and manipulate them that way, because they are understandable by a single model. And then there's other ones like ImageBind, which I won't get into today, but it's basically another multimodal model. I believe it's capable of 8 different modalities. I forget which ones. So it's image, video, text, accelerometer data. It's able to do thermal data. Oh gosh, I'm definitely forgetting a few. But yeah, I don't think it does smells quite yet, but it's really impressive. And these models and these cross-modal capabilities, getting these models towards what people can do in terms of understanding words and understanding what's happening in the world around us. See how we're going for slides. So why vector searches? Well, this is a thing. Search is really, really hard. And search is one of those things when it's done poorly, you notice. I don't know if you're old enough to have used things like Alta Vista, which was a keyword search across the internet. It's super painful. So it's one of those things where if you have to know the magic words, in other words, if you have to know the exact words people used, It's difficult with semantic search. You don't need to do any of that. So vector searches are very useful because they're robust to things like synonyms, word forms, and typos, and they work across languages. That's really cool, and modalities. And again, they're powered by these models that generate vectors. And that's why when people talk about AI, quote unquote AI native, that's what they mean. I will say as a personal caveat that I have mixed feelings about the use of the word AI because it's such a vast field, and I think these days it gets used to basically mean language models. Obviously, we know that AI isn't just language models. But I think in this context, when people talk about AI, it's language models in terms of, models to generate vectors, and more in a more popular culture, it's going to be language models, or at least large language models like your GPTs of the world. And that's probably a good segue for one of the other demos that I have, which is this guy. And yay. Cool. Yeah, let's hope that works. Cool. So have you all used ChatGPT? Hands up if you have, please. Fabulous. That's what I typically see. So before, when I said I do surveys when I go and do conference talks, I ask people if they use vectors, and like 5% of the room would say yes to that. And when I asked about ChatGPT, it's usually like 99.9%. Have you all used the GPT-4 or 3.5 API? A few of you? Oh, that's cool. So I've done something like a fairly simple dumb demo here just to talk about what retrieval augmented generation is. So let's see how we go with that. So this is just a really dumb helper function that I cooked up earlier today. But basically all it does is instantiate a connection to OpenAI with my key. I'm using the latest GPT-4 Turbo model. I used to not use GPT-4 a lot for demos because it could be a bit slow. GPT-4 Turbo tends to be pretty fast from what little I've tried, so hopefully it does okay. Every time I do demos, though, something goes wrong with an API. So far, it's been okay today. Let's hope that it goes well. I've just got a short custom prompt here. It says, you're a helpful assistant who provides short, to the point, well-written answers without verbose caveats, because it tends to go on and on sometimes, and it's not great for demos. So I've just asked it to give short answers. Cool. So you've all used ChatGPT. I use it a fair bit for various things as well, and it's great. It's great for producing bits of knowledge that are relatively well known. So here's things like this, right? Explain how a vector embedding works in just a couple of sentences, and hopefully it hasn't done a better job than I have. It says vector embedding represents objects like words, sentences, or images as points in high dimensional space, such that spatial relationships between these capture some semantic or contextual similarities between the objects. A little bit academic than what I personally prefer, but it's fairly accurate, right? So high dimensional space, as in it's whatever number of dimensions, like 1,500-ish in OpenAI case or what have you. And in terms of in natural language processing, words with similar meanings are positioned closer together. So that's what we spent the time talking about. And I can ask it for relatively specific things like, hey, how does Weaviate store vectors in its index? What kind of tools does it use to improve efficiency? And I've said, hey, just tell me those in a few bullet points, because when I tried this earlier today, it was giving me a long description that I'm sure you have no interest in reading, and I don't really have all that much interest in reading out myself. So it says it has a vector storage, cool. It does ANN, that's great. It does vector pruning, not sure what that means, and batch indexing. And one thing about these models, these large language models, is that they are stochastic. I think with the latest API, you can seed them I'm sure if you've used data science libraries, seeds in NumPy, right, to control the randomness. So I think you can seed them at the moment. But you can see when I run that query again, it gives you a slightly different set of results. So there's stochasticity and there's like other parameters you can tune, things like temperature. So just keep that in mind every time you use these tools, that it's not a deterministic thing like when you're using, programming languages most of the time. Okay, so let's ask, hey, what kind of compression technique does Weaviate apply? Because sometimes it's not doing that today at the moment, but some of the questions, sometimes when I asked about it, it was saying, oh, actually, Weaviate applies compression to the vectors, blah, blah, blah. So it actually, when I ask it, this says, oh, Weaviate applies approximate nearest neighbor indexing to compress and store vectors efficiently. That's interesting. And it's starting to backtrack and says, oh, this doesn't compress the vectors actually, but it optimizes the storage and querying of the high dimensional vector space. And are you familiar with the phenomenon of what's called hallucination with large language models? Right. And it's the idea that these models are trained to produce some sort of answers, so that when you ask it to produce answers, which is what you're doing by asking a question, it's very unlikely to say, I'm not sure, it'll just give you an answer, right? And it could be quite correct or quite, relatively reasonable. Like when I ask it, hey, how does a vector embedding work? Because there's a lot of information about this in its training corpus, right? So all of its, the model weights are basically such that it, quote unquote, remembers a lot of information about how vector embeddings work. But if I start to ask specific or recent questions like, hey, what kind of compression technique does Weaviate apply? Or, always plays the crowd, how many drivers' championships has Max Verstappen won? Max has won 2 championships. And depending on how many of you follow Formula One racing, you probably know that that's not true. He's won 3. So how do we fix that? Something called retrieval augmented generation is a solution for this problem. And what I'm going to do is this. So have you done this thing? Have you used RAG before in your workflow at all?
I don't think we have used it before.
You use large language model before.
We have in LLP course, but yeah, I'm not sure if taken it yet. But I don't think we have used RAG dataset before.
Okay, that's good. Okay, that's really cool. Sorry, I just wanted to make sure I'm not like talking at you about something you already know. So you might have done something that is essentially RAG in a fairly manual sense. You might have used ChatGPT to paste a bunch of text, right? And say, based on this, tell me X, Y, Z, right? You might have like pasted a bunch of like lecture notes, because I've certainly done this with like some textbook stuff I don't understand, or paper, and said, can you summarize this? Or what does this mean in plain language? You've probably done stuff like that, right? And that's essentially what RAG does. And just keep that in mind as we go through this process. So all I'm doing here is I've got some text from our documentation, actually. Oh, that's the wrong file. What's the file called? Sorry, just bear with me. F1 context. So what I'm doing here is I'm just loading a text file now from the right one into an object. Just it's F1 context. That's all this is. It's just a bunch of text. And I'm going to ask it again. And I'm going to say, hey, I'm going to ask the GPT, using my helper function, how many drivers' championships has Max won? Tell me in a very short answer. And I think I've just added that as a parameter, so I should be able to do that. And let's see what we get. So it says now Max has won 3 drivers' championships. Whereas just before, as of my knowledge cutoff date in April 2023, Max has won 2 championships. And all I'm doing here, not response, F1 context, is all I've done is I've gotten an excerpt from Wikipedia, just using the Wikipedia API. So that's all I'm doing is passing a bunch of information that provides it with some context or knowledge right? Because the large language model is very good at understanding or processing text and synthesizing text out of it, but it's not able to access knowledge or access up-to-date information because the model is frozen at the end of its training. So this is called retrieval augmented generation, and it's quite a common technique now to overcome the problems that we're just talking about. And I can do the same thing with Weaviate. So I can say, load up this Weaviate context, and I can bore you with all the technical information from the Weaviate website. And basically it's like, you know, it's from one of our pages, right? So why index data as vectors? And if I look for the word compression, not a huge fan of Jupyter, I'm not gonna lie. I usually code in an IDE, but it's easier to do these demos in Jupyter. But yeah, so there's information about what's called product quantization. And you can see that there's a section where we talk about compression in here, right? So all I'm doing here is to pass that information to the API by passing the context. So I've changed the syntax for my helper function in this object as Weaviate context. And the question is the same as before, right? So, need to actually get the same, need to get the same question as before. What kind of tools, compression technique does Weaviate apply to compress vectors? Oh, sorry, I had the right question. It's the next question that I was thinking about. And it will take a little bit longer because the input text is longer. So now it says, it starts to give me more specific answers. Weaviate uses HNSW for vector indexing, which is the index that I just talked about in our talk earlier. Has all these index parameters. And now it says, oh, here's this thing called product quantization for compression. And that's something that we've introduced into our software library like 2 months ago, something like that. So it totally makes sense that this information is not available as part of the training corpus in GPT-4, but it has no way of knowing that, right? It's not self-aware. It doesn't know what day it is. It's just a neural network that takes a bunch of inputs and it produces output text. So by providing this information and grounding it in basically knowledge, we're able to separate out the part of the model that synthesizes text and produces outputs versus a store of information, which is what our database is. And what I'm doing here is, of course, not using a database, but just reading a text file, right? And passing it through. But essentially, that's what retrieval augmented generation does. So this is a demo app that I built, a couple of months ago for a different talk. Fun fact, I started building this on a train in London because I was going to a talk, and then someone said, oh, you should have a front end. And I was like, I don't have a front end, but I do have 40 minutes. So I started building this. And what this is inspired by kind of my laziness because, I always say there's way too much content and I don't really have time to watch them all. And I said, hey, what if I didn't have to watch all of that? What if I could just get a video summary and ask the video whatever I want? So here are a bunch of videos. So not many, but just, for a demo, it's good enough. So here's a video of an interview with Margot Robbie, Andrew Ng's interview. Here's Connor's explanation of what's called Gorilla. Video game review, which was new at the time, and a Stanford lecture. What I've done is to build a RAG system that you can use to talk to these videos. So I can, for example, get a summary of each video. And this is all dynamically generated. So I can say, oh, what's this video about? Well, it's about Margot Robbie's involvement in the Barbie movie, working with Ryan Gosling, and Margot's requests for the film. And I can also speak to, quote unquote, speak to the video. So I can say, what are some of the themes that are explored? And in a RAG system, I wouldn't necessarily manually pick the context to pass to the API. So in my simple demo earlier, I was actually using the API to automate-ish what I might do with a ChatGPT interface, right? So I was feeding it a question as well as a bunch of information to ground it. Here, what I'm doing instead is to use a database. And when I run this search, what's happening under the hood is I've got it to perform a search and find these chunks of text based on my query, right? So it finds these chunks like Margot Robbie talking about, oh, we're exploring things about how anyone might feel, yada, yada, yada. And Barbie, not thinking about death because the whole, sorry about spoilers if you haven't seen it. It's a really good movie. But it finds these bits of text. But then you're not just getting these bits of text back. What's actually happening is I'm using the language model. This is GPT 3.5 under the hood, and say, oh, actually, some of the themes explored in the source material include all of these parts. So even though the language model wasn't trained on any information or has any idea really what was in this interview with Margot Robbie that was, June or something like that this year, right? We're able to feed it the right information, and we're able to explore and synthesize the data that comes back from the database. And what that does for us is to transform a database from just being a repository of information, right? Because you used to think of a database like a library. You have to go and find the information. And the best you can do is to get the source material. But now you can combine that with this amazing language model, amazing tool called the language model, and transform the information before it comes back to you. So think about a lot of the workflows that happen, like if you, the kind of like the classic, hey, you're a junior in Office XYZ, read these reports, summarize them, extract key points. Well, you can automate a lot of that, right? And then maybe you don't go all the way and say, produce the final report, but maybe you can say, oh, these are the documents you want to look at first. These are the key points, and you can verify that information too, because a part of the challenge with a language model is that they're not, it's very difficult to dig into what's happening under the hood in a neural network at the moment. There's people working on that area, right? But it's not able to interrogate backwards and say, what was in the corpus? Why is the output the way it is? But if you have the source material, you can actually provide and have traceability as to why it's producing the outputs it's doing, because you've given it the source as well as the kind of linguistic tools to manipulate the source. So those are the reasons that people use RAG. And if you want to explore using RAG, this is slightly old syntax because we've got a new API out, but this is kind of essentially all the code there is to perform the queries that I'm showing you under the hood. So, it's not all these tools that exist just in the same way that, if you're using, if you're doing matrix multiplication, you can just use NumPy and you don't really have to know how to do it. It's kind of the same thing with these tools that abstract away a lot of these things. We've gone from tools, even in machine learning, to go from things like TensorFlow to tools like transformers, where it abstracts away a lot of the difficulties in using deep learning models. And the same thing is happening with using language models, with using vector databases and things like RAG. So that's a little introduction to RAG. And again, we talked about the vector data search pipeline where this happens. And when you add a language model to it, this is the process. So on the left-hand side, you still have your user performing a query to the vector database to get some stuff back. But then at the same time, what that data is used for is actually to prompt the language model with that context and to get that response. And this diagram actually even, I would say, is maybe not super accurate, because what actually happens is the vector database directly prompts the language model with the context. So there's no extra latency in terms of, it's not coming back to your computer if you're dealing with a remote database, to then go to the large language model and back. So the vector database directly contacts the API and it comes back to you. So if your latency is kind of a key target, then it's an efficient way to do things. So it's inherently a two-step process of data retrieval, as well as sending that data and the prompt to the language model to get the results back. I won't go through that, some example syntax. So one of the things that I personally use it for is actually for embarrassingly digesting papers, because I find that papers are a little bit longer than I would prefer and a bit dense. So quite often I would get a high level summary and go, do I want to read that? Yes, no, maybe. Which part of it do I want to read? And get some summaries and ask questions. And it works quite well. And I'm starting to see these tools get integrated into certain apps. Like if you use apps like, I use an app called Reader. So it's like a read it later app. And they have tools now where it's integrated and you can ask the document a question. And that's, I don't know exactly what their tooling is underneath, but that's exactly what it does. And for work, I create like educational material. And where I find tools like this is really useful is for transforming. So it's not so good at creating original material, but for creating like derivative material. So I would write a bunch of material and say, oh, write me some revision questions that'll help students with this or readers with this. And that's really great for that. Or if I want to if I have a bunch of papers in my database and I want to find which papers talk about XYZ topic, that tends to work quite well too. So that's really cool. A key consideration when you're performing RAG is this idea of chunking. So I talked earlier about how a vector database, each object gets saved as a vector. So what that means is that each object that you get back is based on a vector. And, if you're performing research or doing research on Google, and if Google said, oh, go and look on this domain, that's not going to be so useful, right? You kind of wanted to say this page. And these days, Google searches will say, actually, here's the relevant passage for you from this thing, right? So, and that basically in the same idea applies when you perform vector searches and build a vector database. You want to design your database such that the granularity of what you get back corresponds well to what you're searching for, right? So if you want to find just an article, that's fine, vectorize the entire article. But if you want to find certain passages back, you want to cut up your article or book or whatever into smaller passages of 100 words, 200 words, paragraph, or whatever kind of works for you. And that's called chunking. And as a rule of thumb, I think about, what I've seen is that chunk about 100 to 200 words as a starting point works relatively well. And then go from there. But it really depends on what you're trying to do and what your source data looks like. But it is a really important and interesting topic. And because if it's too granular, like getting a sentence back out of context is not that useful either, because you might just get a sentence that says chunking is really useful. If you search for chunking and then you're like, so what? How do I do it? It's not that useful, right? So you want a whole paragraph back, or you want a section. So it's something to play with. But that's what the advice I've seen is somewhere between 100 and 200 words as a starting point, and then go from there. Cool. So, and why is RAG something that is associated with vector databases? Well, one reason is that basically a good search or a good search is a key for a good RAG system. Or conversely, if you have a bad search system, your RAG system is going to be horrendous. So all the challenges of finding information in basically like our swarm of data. So a few years ago, one of the sort of buzzwords or buzz phrases was big data, right? People talked about, oh, everyone's got big data, yada, yada, yada. I think where that's really come in is that being able to find the right information has become really important, because I think I saw a stat that, every day, and this is just a couple of years ago, we produce basically an Eiffel Tower's height of Blu-rays worth of data every day. Like, that's how much data gets produced. I'm obviously not on Blu-rays because that would be silly, but like a crazy amount of data gets produced every day. So even within an organization, you have amounts of data. I mean, I know personally, I have more data quite often on my computer and on my cloud drives that I know what to do with. I have trouble finding stuff. So if you can imagine performing search and you can't pass all of your entire knowledge base into the language model, you have to find the right data that's relevant, right, and up to date to the RAG system or to the language model for it to generate the right answers for you. So being able to perform a search that's performant and of high quality is really important. And that's why these vector databases have come into vogue, been highlighted along with the rise of language models, at least in my opinion. Cool. So that's kind of it. I know I said I'll speak about the recommendation systems, and to be honest, I haven't had a lot of time to prepare for that part of it, but I did, and I did actually read these papers. I didn't just get the language model summarize them. There are some good papers out there in terms of using large language models for recommendation. So, just before we started, we talked about collaborative filtering and different ways that classical machine learning does recommendation, right? So I think there's been some efforts recently to use large language models for recommendation. And one of the ways to do that has been basically to get the language model to straight up produce like outputs in words to say, hey, these are the recommendations I would produce for this type of user, right? So you give the language model that's maybe fine-tuned or maybe had some context, like in a RAG system, information about the user, and say, well, what would this person like to do? Is that me giving the thumbs up, or where did that thumbs up come from?
It's a feature inside MacBook. So whenever it detects like a thumbs up, it will draw like a thumbs up button. Yeah, like this one. But I have no idea why. Probably right now it's lagging a little. So
that's amazing. I'm just trying to find this. I'll maybe send a. Oh, here we go. Sorry, I'm looking for my colleague's post. I'm going to post this here. So this is a post from my colleague Leonie, and what she put together here is a recommender system that uses RAG. And what she's done is to build a system. So let's say I'm a huge geek, so I love like superhero movies, but let's say something like that. Here's a kind of recommender system that will just recommend something that's similar to what you're looking for. I was hoping that the search string would. If I search, I'm going to copy that. And if I look for it in semantic search, what just happened? Okay, cool. So if I search for the Grand Budapest Hotel using semantic search, I get these similar results. And where I'm going with this is that it depends on what you're trying to do with the model, like in terms of your recommendation. I guess in system design, you want to, or in any kind of problem solving, you want to think about what it is that you're trying to achieve. So if you want to produce your recommendation system that will recommend movies based on a similarity of something, a semantic search might be a really good way to go about that, right? And you can do this by, say, doing things like inputting your plot if you can imagine inputting your keywords or that like describe the genre of the movie or the particular theme that it explores or what have you as a description. And if you have a database of those things, you can get similar objects back, and which is what this is doing. I think this is doing it based on the title. But if you want to do something that's a little bit more like collaborative filtering, which says, hey, I've got information on these types of users, and they tend to like these other types of movies. And it's not based on similarity, it's more, matching of characteristics, right? Another way that I've seen people do this is to use a vectorizer model to produce embeddings, and those embeddings become part of your input features, right? So in collaborative filtering, you have N features in classical machine learning, and then you might tack on some number of additional features that say describe the user's characteristics or the, whatever. And you don't now have to worry about capturing those words as categories, right? So you don't have to like, hey, like they're like a 5 for thrillers and like a 2 for horror movies, but like 8 for romance novels or romance movies or whatever, right? You can just like capture those in words and output those words into an embedding. You probably don't want like 1,000 features. You probably want to do some sort of dimensionality reduction so it doesn't like completely overwhelm the rest of your features, right? Because you don't want 15 manual like features that you've engineered and then 1,000 vector embeddings. That's going to just overwhelm everything. But that's something that you can do as well, is to output some vector embeddings and then combine that as part of your input feature set. So there's like different approaches you can take in terms of making use of these language models and how you go about it. And look, I won't pretend that I've done a lot of research in this area, but these are some of the approaches I've seen. So hopefully that's useful. But that I can imagine also using a hybrid approach where you recommend some movies based on similarity and some movies based on your classical kind of ML approach with, collaborative filtering or what have you. I'm also cognizant of time, so I'm happy to hang around and answer questions as well, but I don't want to hold you hostage. I'm sure you got like better things to do than listen to me drone on, so I'll stop there. But yeah, happy to take any questions and have a chat.
First of all, I want to say thank you to JP for giving this wonderful presentation, and let's give him a round of applause. If you have any questions, okay, I don't think anyone has any questions. But
okay, cool. What I'll do is I'll send the slides over later today, and then and let me know if you have any questions or whatever afterwards too.
Yep. Okay. Thank you very much, and have a nice rest of the day, and we'll talk to you later.
Lovely to meet you all. Thanks for listening, and good luck with everything. Cheers.
Thank you.
Thank you.
Cheers. Bye.
Bye. I have a lecture.
Let's roll.
Actually, I have a question.
Yes.
I was just looking at the notebook that you provided.
On Kaggle?
On Kaggle, yeah.
It's an old one, right?
What?
It's an old one, you mean?
I mean the natural language processing one. Like the one that...
Yes.
Yes, this one. I'm just like very curious about this like for loop. What does it do exactly? Especially like this. Because
Yes. So this is the model way. This is grouping by genres, right? Yes. Yes. Have you watched the lecture?
I did.
Okay. So basically, this for loop goes through every user. And first of all, there's a function. Are you familiar with pandas?
Yes.
Okay. So X is a table that you have with training.
Yeah.
And so it groups all of the users, and now user ID is the ID of the user for each group, and the group is like a big table. It's a subset of the whole table where the user ID is like the user ID.
Yes.
And then what we do is we find all of the animes that are present in this group. So basically with then like yeah, if it's 0, then we just skip it.
Mm-hmm.
And so that for that user, it means we don't really have a representation of an embedding
Mm-hmm.
because like we don't have any matches.
Mm-hmm.
But if we do,
Mm-hmm.
then we select the columns from the anima table,
Mm-hmm.
and specifically the ones that are after 4. So those are only genres,
Columns, yeah.
and then we just meet them.
Okay.
And what that does, it basically gives us a prototype of what this user likes as genres.
Yeah. But the genres are like one encoded, right?
Oh yes.
What does the mean there?
Yes. So then like it will be like an average genre of sort of that he
Okay.
likes. So for example, if you like 2 games which are like shootings and
Mhm.
one of them is like cars,
Mhm.
then you will have like a higher weight for shooting games than for cars.
Right.
So this is kind of the idea behind
Mhm.
that. And yeah. I hope that made sense.